Our lives are filled with diagrams. They help us see things better, even math. What we're going to talk about today, well, is a graphical representation of those sets that we talked about in a previous lesson. And that graphical representation is something called a Venn diagram. Now, a Venn diagram consists of a couple of components. The first component, the most important component, the outside component, is represented with this rectangle that is referred to as the universal set. Now, the universal set is the set from which other sets or subsets are created. It might be things like the alphabet. So if we were looking at vowels, right? Vowels is a subset of the alphabet. Positive integers is a subset of the integers space. Even positive integers is a subset of the positive integers and so forth. So really, the universal set is the set containing all the objects or elements from which we are deriving these subsets. Now, whenever we did this set builder notation in the previous lesson, we talked about this set builder notation. We had something like A is an element of the positive integers where or such that, we'll just say A is even and A is less than 100. All right. So this right here is defining what our universal set is. All right. So we've got in this case, the universal set would be positive integers. Now, we also graphically represent the sets themselves. So inside, we are going to put, and we have to label it somehow. So the label may be inside of the circle, the label may be outside of the circle, the label may be outside of the circle with an arrow. I've seen any number of different ways of representing this, but basically that circle is going to be labeled with the name of the set. All right. And typically the subset inside of the universal set, the set, is going to be represented with a circle or an oval. But according to the original definition, it can really be any sort of a graphical element, a graphical shape. All right. And just because I've got a set doesn't mean we can't represent multiple sets. For example, I may have another set here, B, another set here, C. And the relationship of them, how the circles overlap or don't overlap, show how the elements are shared between these subsets. Now, in this case, each one of these sets doesn't touch the other sets, any of the other sets. So these are what we refer to as disjoint sets. There is no common element between those. But let's say that we have another subset, let's say D, that does share some elements. And so this overlap here represents the elements that are shared by both A and D. Now the areas that are not overlapped, those are the ones that are not shared. So where we have this space right here where A is not covered up by any other subset, those elements are unique to A, not contained in D or B or C. And likewise for D, in this area right here where we don't have anything overlapping that portion of D, those are not shared elements. But where the two overlap, that is shared. One of the things that we did talk about was, well, I kind of gave an example of the vowels within the alphabet, right? Well, I'm not really happy with that example, and I'll tell you why. So if I draw the universal set, and the universal set is the alphabet, right? And inside of here, I have something called vowels. That's a subset. And that would be A, E, I, O, and U. I do not like this example. Why? Because many of us have learned from our elementary school that the vowels are A, E, I, O, U, and sometimes Y. And according to Merriam-Webster, Y can be considered a vowel sometimes whenever there are no other vowels, for example, in rhythm. R-H-Y-T-H-M. There's no other vowel, so the Y has to serve as the vowel. If Y is at the end of a word, like story, or at the end of a syllable, cycle, those would also be considered vowel instances of Y. Or if Y is in the middle of a syllable, for example, in system, that sys that Y is a vowel. But there are other times, like in yell, that Y is not a vowel. So what do? You say Y is like half in, half out. Sorry, not legal in terms of a Venn diagram. So what a better example might be is if we said, let's create a set where the set X is equal to little x in the alphabet, right? Where X is contained in the word discrete. And so in that case, we can draw very distinct Boolean membership in this set. What you'd have is the D, the I, the S, the C, the R, an E, and a T. We only need to have one of the E's because that's in there, right? And so that will show a Boolean representation, right? Either it's inside the circle or outside the circle. A, Q, U, V, W, all those are outside the circle, a very definite membership, right? All right, let's go and do another example. Let's say that I have 3 sets. I'm also going to do this using set builder notation. Let's say that A is equal to, or A is made up of elements A that are contained in the positive integers where A is even and A is less than or equal to 12. All right, so that's going to give us, how about, so positive integers, 2, 4, 6, 8, 10, 12. Now let's say that B is equal to the set defined by, where B is an element of the positive integers, and such that B is less than or equal to 6. So that's going to give us 1, 2, 3, 4, 5, 6. All right. And then C is going to be made up of, from once again the same universal set, so we're going to always have the universal set of the positive integers, where C is such that C is divisible by 3. All right? All right, so there is our definition. And let's go ahead and list these out. So we have 3, 6, 9. Oh, sorry, it'd be helpful. This would go on for a little while, wouldn't it? And C is less than or equal to 12. All right, so and 12. So our universal set, should have left myself more room, and we have the set A, we have the set B, and we have the set C. All right. And what I'm going to do is just go through each one of these sets and identify which ones are members of which set, right? So, in fact, let's just go ahead. It seems that everything is, we're looking at anything that's less than 12. So let's just one at a time go through each one of the integers from 1 up to 12. So 1, well, 1 is only in B. So 1 is going to be in B. 2 is in A. 2 is in B, but it is not in C. So it's an A and B, but not C. All right, so we have 2. What about 3? We have 3 is in B and 3 is in C. So it's in B and C, but not A. So 3 is over here. 4 is in A. 4 is in B, but it is not in C. So A and B, but not C. So it goes there. That's where it lives. 5 is not in A. 5 is in B, it is not in C, so 5 goes in B, but not A and C. That's that region right there. 6 is in A, 6 is in B, 6 is in C, so it's in all 3. So this area right here where they all overlap, that's where 6 goes. 7's not in any of them. And so, while I am not going to do the entire universe the universal set of the positive integers, I am going to identify 7 as not existing in any of the 3 groups. So I'm going to put it in the universe, but not in any of those sets. 8 is an A, not B, not C. So 8 goes in A, not B, and not C. 9 is not in A, not in B, but it is in C. So we've got one number, 9, that is in C, but not A and B. Then 10 is in A. That's the only place it is, so 10 goes in A. 11 is not in A, not in B, and not in C. So 11 is also in the universe, but not in the universal set, but not in any of those 3 sets. And then we'll go with 12. 12 is in A, and it is in C, but not B. So it goes right there. And that'll give you an idea of how this is all kind of laid out if we define our sets. Now, the thing that's really cool about Venn diagrams is they're not meant to be methods of representing sets enumerated out this way. In other words, this was kind of nice to be able to show how the different elements are landing in each one of the sets. But the key is that really the Venn diagram is meant to be a more universal abstract way of representing the relationship between all of these, each one of these sets. I'm going to make some room on this board. We'll go to the next thing. In our introduction to sets, we talked about some relationships of sets. So for example, we talked about A being a proper subset of B. And what that meant was that A is a subset of B. Every element in A is contained in B, but it is not equal. They're not equal. So if A is a proper subset of B, that means that B has at least one element that's not in A, but all of A's elements are in B. And then we talked about A being a subset of B. This underline here means that it is possible that they're equal. So A is a subset of B, but it's possible that every element of A is also an element of B. They're equal. And that led us to A is equal to B, which means that every element that's in A is also in B. And then we also had A is not a subset of B. Now, how do we represent these things with Venn diagrams? Well, in the case of a Venn diagram, what you've got, first of all, we'll do the universal set, right? And in this case, the universal set, we're just talking about this in abstract terms at this point. And whenever we say that A is a subset of B, what we've got is that B contains A. So everything that's in A is in B. But this idea that we have a proper subset means there is at least some portion of the set B that is not contained in A. Now, whenever we go to the subset, A is a subset, then we also include the possibility that A is equal to B. So this figure right here, the figure of the Venn diagram that's represented by this satisfies. So this Venn diagram, not only does it support A is a proper subset of B, but it also supports that A is just a subset of B. But there's another Venn diagram that could possibly represent this situation, and that would be the situation where you have A and B, so I'll have A and B, they're exactly the same set. And so this is the notation that I've seen in the past, this arrow showing that we've got a single circle, but really what it is 2 circles that are exactly on top of each other. Every element that's in A is also an element of B. So this really represents the A equals B, but it could also be the case where A is a subset of B because it allows the equality. Now, A is not equal to B, or excuse me, A is not a subset of B. Well, there are a number of ways that this could be represented. So let's draw some of them here. First of all, the most obvious would just simply be A and B are disjoint. They're distinct sets. They don't share any elements. They don't have any elements in common. That would mean that A is not a subset of B. But it is possible that they share some elements. So I could have that A and B do share some elements, but there are some elements of A that are not contained in B. Once again, this means that A is not a subset of B. There's a third way this could happen, though. And that third way would be that B is actually a subset of A. So in this case, A is not a subset of B, but B is a subset of A. So that is, all three of those are possible representations for this A is not a subset of B. All right, let's do another example. Now, let's say that we have a little company. It has some online resources. We have three methods to access these online resources. We've got a phone app, we've got a browser, a web browser interface, and a dial-up phone system. All right, and that's three of the ways that our customers can access our online resources. Problem is we've had a really bad year and we can't afford to support all three of those. So we need to kind of cut one of them off. How are we going to figure out which one to cut off? Well, we don't want to cut off the one that's used the least. We want to cut off the one that has the least amount of users that use just that one. So we want to alienate the fewest number of customers. So let's just come up with some details here. Let's say that our total number of customers is, let's say 1,592, all right? Now, as far as the app is concerned, 952 of our customers use the phone app, all right? The browser, let's see, 949 use the browser. Dial-up, we've got a whole 831. So there's the breakdown. But understand that some users use two of them. So we have some users that use the app and the browser, some users that use the browser and dial-up, some users that use app and dial-up, some that use all three. So what we're looking at with our Venn diagram here is I've got, let's see, I'm going to say A for the app. We'll just say B for the browser and D for the dial-up. All right, and the universal set is our customers, all of our customers. And in this case, it's, what did we say? 1,592. All right, now there are what, 1, 2, 3, 4, 5, 6, 7, 8 regions here. We have the outside, the region that is not contained in any of the subsets. Those are our customers that don't use any of our online resources. We're not worried about them. Be nice to figure out how many there are, though, so we'll do that in a minute. Then I've got this region, which only uses the app and nothing else. This region, which only uses dial-up and nothing else. This region, which only uses the browser and nothing else. And those are the numbers we are hunting for, because the one that the lowest number here is going to be the one that is we absolutely cut off the least number of customers. We can't quite figure out exactly which one of these is going to be lowest without figuring out these regions in here. So we need to know a little bit more information. And some of the additional information we have is, first of all, we know how many of our customers have used all three. All three, that's this region right here. All three, well, 321 have used all three. And in fact, we can just go ahead and write that inside here, 321. Now, we don't know exactly how many have used the application and how many have used dial-up only without using the browser. But we do know how many have used the application and how many have used the dial-up together. So this whole area right there. So this is, they've used at least the application and the dial-up. And the ones that have used the application and the dial-up are 577. All right. We also know how many have used the application and the browser, but may or may not have used dial-up. So application and browser, just the application and the browser is 614. And then we know how many have used the browser and dial-up, but may or may not have used the application. So browser and dial-up, well, the browser and dial-up would be 366. All right. Now, can we figure out these regions here and subsequently these regions here? Yes. Turns out that since we know how many have used the application and dial-up, and we know how many people have used the application, dial-up, and browser, all we do is take application and dial-up and subtract 321. So 577 minus 321 is 256. All right. Can we fill out this space? Well, yes, we know how many have used the application in the browser, and we also know how many have used the application, browser, and dial-up. So application and browser minus dial-up, that's 614 minus 321, that is 293. How many have used the browser and dial-up but not the application? Well, that's how many people have used the browser and dial-up minus the ones that have used all three. So that is 366 minus 321, which is 45. All right. Now, can we figure out which one of these is the lowest? Well, how many people have used the application? We know that 952 have used the application. So 952 minus 23 and 293 minus 321 minus 256, that gives us 82. How many have used just dial-up? Well, that's how many people have used dial-up minus 256 minus 321, and then minus 45. So 831 minus 256 minus 321 and minus 45 is equal to 209. And then how many people have used only the browser, this section down here? Well, that's 949 minus the sum of 293, 321, and 45, and that gives you 290. All right. So by a long shot, it looks like the application, the users that have only used the application is the low number. So it looks like the one we're going to cut support for is the application. Actually, but look at this. It was actually the one that people use the most. Now, this is kind of, maybe this is not quite the best business decision, but it's just one way that we can kind of get some additional information using a Venn diagram. And by the way, there's another piece of information we can get. We can figure out how many users don't use anything. Well, the total number of customers that are not using anything at all is 1,592 minus the sum of the numbers in all of those regions of the subsets. So it's 1,592 minus the sum of 82, 256, 209, 321, 45, 293, 290. All right, and the result will be 96. Now, by the way, oftentimes whenever you see Venn diagrams, we use shading to represent the portion of the Venn diagram that we are interested in. For example, we were interested in the number of users that use the app and nothing else. And so we might use some shading like this to represent that particular region. In a later lesson, we're going to use this method to describe certain operations on sets.